Now, based off of that information, can I give you the general characteristics on how to define a fluid? So general characteristics of fluid flow. Remember, we're not defining fluid elements, fluid particles anymore. We are now talking about fluid flow. Good? Now that we have defined that we are going to use Euler's methodology of fluid flow instead of Lagrange's methodology of fluid particles, we are going to have to redefine what we mean when we say different things. So number one, fluid flow can be steady, unsteady, or they could be turbulent. So in general, fluid flow is defined by density, flow velocity, rho, and flow velocity v. Is that what we said up there when we were defining fluid flow? That they are defined by density and flow velocities right here. So when these two things are constant in time, we call that kind of a flow steady. When these two terms change with time, we call that flow unsteady. And when velocities change erratically from point to point, we call that kind of a flow turbulent flow. So for this one, low flow velocities. This condition happens for when the flow velocities are small, low. So for example, streams. You know those little meandering streams that sort of go slowly over time? Streams. Slowly flowing over time, just meandering their way down the hill. These ones are usually like rivers. Some places they get faster, some places they get slower, but it's sort of predictable. You can sort of guess where the fall will come. It's kind of slow, steady change over time, right? Turbulent flow, this will be like Grand Rapids. What happens there?
Water moves all over.
It's all over the place. It hits rocks. It hits itself. It hits the sides. It goes down very suddenly. There are lots of waterfalls. That's called a turbulent flow, where anything can happen at any time. So, for example, waterfalls are examples of turbulent flow. And then rapid. Turbulent will be when it goes over like rocks. So it hits a rock, eddy currents will form, and things like that. Like, for example, smoke rising, turbulent. Right? It goes everywhere, and you can't predict it. You can't write an equation for it. Number two, fluid flows could be compressible, or they could be incompressible. When they are compressible, what happens to density? Changes. When they are incompressible, density remains the same. What kind of a fluid is where density can change easily?
Yes.
There we go. What kind of a fluid is where density sort of remains the same no matter what you do? Liquids, water, for example. Like if you compress it, yeah, maybe a little bit, but not really the density. So liquids remain the same. Number 3. Fluid flow can be viscous or non-viscous. What is viscosity? So think of viscosity. Oh, I should probably write eta. So think of eta as friction in your system. It is the opposition to the flow. So your system, your flow could be viscous or it could be non-viscous. When it has a high resistive quantity, it is called a viscous flow. So what would be a viscous fluid? Honey would be a good example, right? Whereas what would be a non-viscous flow?
Okay.
Also, gases. Gases flow easily, right? You just let them go, push them a little, and they start flowing. That's why steam is easy to transfer through pipes rather than water. Okay, so viscous flow, think of viscosity as being equivalent to friction. And viscous fluids have large eta, and non-viscous flow have small eta. The last one is the most interesting one. Fluid flow could be rotational or irrotational. And that's the one that confuses everybody. So irrotational flow is where the curl of the velocity equals 0. Whereas rotational flow is where curl of velocity vector is not 0. What do I mean by that? So in this case, when you have an irrotational flow, even if you have things going in a circle, look at these arrows. Are they equal at a particular circle? This is an irrotational flow. Whereas in order for something to be rotational, the arrows need to do this. So I'll give you an example. If you have this flow, and there is a bug in here, if the water turns, so for example, this flow becomes, instead of going like this flow becomes circular, and this bug starts to go down the drain pipe. This bug is not in a rotational flow because this bug is going straight. But if this bug starts going in a circle as well as the tide turns, then it is in a rotational flow. Okay, so not only does the thing need to turn,
But the other thing needs to turn.
it also needs to turn inside as the bug goes down. That's the difference between rotational and irrotational. Or in our case, we'll just look at the curl of it, and then if it comes out to be 0, then it is rotational. If it doesn't come out to be 0, it's irrotational. Done. When in doubt, use math. Do we all know what curl is, right? Del cross B. We did it before. Last chapter, we did it with F. Now we're going to do it with V.